So I've done a few videos in the past, and I even recently did a blog post on ESD diodes, ESD protection, and general input protection of a circuit board. But I've never done a video, and I haven't seen a lot of information out there on doing a simulation / real world examples of how you protect mostly the input side of a power supply, so the input that goes into your circuit board, from a high voltage transient, either a EFT or, for this video specifically, a surge event. So what I'm going to do in this video is use a kind of quick and dirty online Faustad simulation to show how general circuit protection schemes like TVS diodes, electrolytic caps, items that you've seen probably a lot of but know exactly how they work when implemented in a way that it sees a surge. So I'm going to go through a few of those different protections, pro and con it, and then at the end go over a combined method that works really well to bulletproof a circuit. The surge circuit that I'm going to be using is the standard IEC 660-1 that is specified in the standard. And there's a handful of different ways in which you can generate it, but ultimately, in the one I'm going to be using is the 1.2/50, 8/20. And what that means is the front time, the time from start to the peak voltage, if it is open, will be 1.2 microseconds, and then the time for it to decay will be 50 microseconds. And it's important to note that that's when it's open, so when there's nothing connected. And then if there is a short, it's a very similar waveform, except now it will be 1.2 microseconds and 20 microseconds to decay. Like I mentioned in the intro, I'm going to be using an online circuit simulator called Faustad. And what I want to be very clear about is I'm not intending on this to be a quantitative simulation. I'm not trying to model every single component perfectly. All I'm trying to do is just show a qualitative comparison between different protection schemes. So the circuit for the surge generator is super similar to what is in the IEC standard. I added a couple blocking diodes just to prevent any ringing and to prevent any backflow into the generator. And for the device under test, or DUT, this is simulating the input and then the general circuit and component load of a circuit board. So I have 10 micro ohm or milliohm resistors to help with showing parasitics. We have a 12 volt supply, so the surge generator will go into this main input. I have a 2 microfarad capacitor to show just general purpose decoupling and whatever capacitance is on the board. And then this goes into a 220 ohm resistor just to simulate a low current draw that is continuous on the board. So if we disconnect the DUT and if I have the switch closed, I have everything on here to be pre-charged just to make it easier to show. And if we start this, you can see that the max voltage is 1.1 kV, which is pretty close to the 1 kV on the second lowest voltage peak for the IEC standard. And then when it gets a little bit further, I'll go ahead and stop it. And the peak is around 1.5, 1.4 microseconds. And then it decays around 50 microseconds. Again, it's just to show big picture what's going on. So now if we connect the DUT, and this is just to act as a control, what happens if we have absolutely no protection, and as you might expect, it pretty much sees the entire 1 kV across here. There's nothing here to help. And what's really interesting is it doesn't really discharge itself. After it's been, after the surge generator has fired into the circuit board, that voltage really has nowhere to go. Now, of course, if this were an actual circuit, it would be arcing, it would be finding shorts through your components. But looking at it again qualitatively, there's no actual defined path for that voltage to go. So if it can't just spin around on the capacitance, it will find a path to dissipate. And that is what we want to prevent. The first element I'm going to show, it's not even really a protection circuit, but it's to show how important just adding bulk capacitance can be. So all I did to this circuit is add 560 mic of capacitance in series with a 1 ohm resistor. The 1 ohm resistor really is just to simulate the ESR, equivalent series resistance, that is within an electrolytic cap. You can also explicitly add a resistor in your circuit to help with ringing, but that's for another topic. So with just that electrolytic added, if we now run this, instead of it showing the full 1 kV peak, it's now down all the way to 356 volts. And what you'll also notice is it decays significantly faster because now we have an actual path and a series element to help burn up this power. One issue with this circuit, other than it still being far too high for most components, is there is a lot of power that is being dissipated and going through this electrolytic. So it's showing upwards of almost 10 kW, which depending on the electrolytic, they're not going to like that. It's such a short event. They could be okay, but you're never really going to want to rely exclusively on an electrolytic for a surge event. It can work really well as a layered protection, but on its own, you're probably going to damage that cap and still almost certainly damage your circuit. The next element I'm going to show, similar to the electrolytic, it's not really a protection circuit or a protection element, it's just a series resistor. And I have it labeled as a series element because this also could be an inductor. I've talked in a few of my other videos about how much I like using series resistors, both on input power supplies as well as signals going to a microcontroller or other parts. So I removed the electrolytic and it's just the 2 microfarad capacitance. So if we hit run on this one, you'll still see, just like with the electrolytic, it's far too high of a voltage. It's still almost certainly going to destroy whatever is on your circuit board, but it's significantly lower than the full 1 kV. And what I want to really highlight is the rise time has been slowed by over an order of magnitude. Instead of it being 1 to 2 microseconds, now it's 15, 16 microseconds, which the slower that rise time is, the less energy that a surge has. So with nothing else on the board, that series resistor can play a really important component in helping your overall circuit. Again, whatever is on here is still probably going to be dead, but it can at least help. And to state the obvious here, I'm not going to be able to do it without letting this discharge. But a big thing to keep in mind with a series resistor especially is, depending on what your output load is, you want to make sure that this resistor doesn't load your circuit and it clamp your current so much that the rest of your circuit won't operate. So a series resistor needs to be sized with whatever the current on your board is, or you could change this to an inductor, which still will help more or less do the same thing, but for DC current, it lets it through, so you're not going to be dissipating that steady state power like you are with a resistor. The next circuit element I'm going to show is everybody's favorite, and that's a TVS diode. I'm not going to go into a ton of depth on what a TVS diode is. I've done a few videos and blog posts about them in the past, but all you really need to know for this is they are essentially a Zener diode that is faster acting and is specifically designed for surges. So they're really good at dissipating a lot of power over a very short period of time. So this TVS diode is rated at a 15 volt breakdown. So once 15 volts is applied on this node, it will start to conduct. I have a 50 milliohm resistor to help simulate the dynamic resistance across here. And that clamping voltage will be higher than that 15 volts. That's really important. So just because it starts conducting at 15 volts, it's not going to limit it to 15. Most data sheets will show, or all data sheets will show what that value is. But for a 15 volt diode, it's going to be somewhere in the 20 to 30 volt range. So with just that TVS diode there, if we run the simulation now, you can see that the max voltage on the DUT is only 37 volts. So whatever is downstream of here might just survive. So you might now be tempted, and ignore this, there's ringing on the surge generator, and my quick way to stop it was just the diode. So it just shows these pulse peaks out here. So everything from this point on, just ignore. So the problem here, and there's always a gotcha when it comes to circuit design, and that gotcha is, look at how much power that TVS diode is expected to dissipate, almost 7,000 watts. And you can get a TVS diode, or especially an MOV, that can handle that much power, but they're gonna be big. It's gonna be challenging if it's a small board to fit it onto the board, and you ultimately still would rather not have a single part handle that much power. You can, and you can put multiple in parallel, but you're typically going to want to do something on top of this to help lessen the amount that that single part needs to take. And an MOV, I didn't specify. You can think of an MOV as basically a TVS diode that has a higher capacitance, so it makes it appear to be a little bit slower, but you can get them rated for much higher power, so they're used a lot of times on AC supplies. So what this circuit really shows, it's the kind of the key about TVS diodes, is unless the diode fails, it will pretty much clamp the voltage to whatever that clamping voltage is. So as long as whatever else you do to the circuit allows this TVS to not die, you're going to protect what's downstream. And that's really important, and it's something I'll come back to when I show the final circuit. Now, the last circuit element I'm going to show is something that you might not have heard of before, and that's a gas discharge tube. And these are really cool parts, and they're very important when it comes to doing surge protection, mostly when you're doing real high powered devices, and especially for lightning protection. So the gist with these guys is you can kind of consider them to be a spark gap. That's also one of the other names for them. And when the voltage is high enough, there's a gas inside that becomes conductive, and it forms a short circuit across this tube to protect whatever is in parallel to this. And there is a really, really big gotcha with these parts, and that is what's called the follow current. It'll also be called the glow voltage, and it's specified here, or the arc voltage, by U3. And what that is, or what that shows, is when this element conducts. So if there's a lightning strike, the voltage spikes up, it's now conducting. Once that element is no longer in use, or once the surge is removed, instead of going all the way back down, it drops to what that arc voltage is, which essentially means unless your voltage is blocked after the event, the gas discharge tube will continue conducting and acting as a short circuit. There's a few different ways you can mitigate this, and the easiest way is just to have something in series that requires a higher voltage to conduct. I'm first going to show what happens if we don't have a series element in series with the discharge tube. So the discharge tube I'm using has a 150 volt breakdown, so when it sees a voltage above this, it will conduct, and the holding current is the follow current I was talking about. So if the current is above this, it won't release. And to illustrate that, if we start the surge, it will peak at 142 amps. The voltage on the DUT is 720 volts, And when I get to the combined circuit, I'll show you why this actually isn't that big of a deal. But the point I really want to show is if we speed this up, so the surge event has stopped, it's coming back down to 0 on the surge circuit and just 12 volts on here, the current isn't 0. So across this discharge tube, there is still current flowing. If I remove this connection, you can see it's just a dead short now, only limited by its internal parasitics. In a real circuit, depending on what these components are rated for, your circuit potentially burns up. It almost certainly doesn't work because you have a dead short here. It might, if you have a fuse here, blow your fuse or just burn up traces. If I get rid of the power supply, wait for the capacitance to drain, now connect the power supply, it's no longer a short. It will function just like it did at the start because that voltage and current was removed from it. So how do we stop that from being an issue? The easiest way is the series element I was talking about. The easiest one to use is a TVS diode again. So if we throw a TVS diode in series with this chain, the Zener diode or the TVS diode I have as a 50 volt breakdown voltage. I'll potentially do another video on just discharge tubes themselves. I don't have enough time in this video to talk about sizing and why I chose 50 volts. But with that TVS diode here, now once the voltage drops below that, it will disconnect this circuit and prevent it from having that short after the surge event. So if we restart this, the surge happens, it limits the current and voltage just like before, except now it disconnects itself from the circuit. So now our current goes to essentially 0. So whenever you use a discharge tube, you have to make sure there is something in series that will ensure that it doesn't stay shorted after the event. Now let's put it together. This could be the protection that you would use if your board is going to have to go through some sort of EFT testing or surge testing. So there's essentially 3 layers of protection. The first layer is the gas discharge tube. Then we go through a series element. This is a 1 ohm resistor. It could also be a inductor. It could be a larger or a smaller resistor, to a 560 microfarad capacitor, an electrolytic with its parasitic ESR, then to a TVS diode with its parasitic ESR. So if we run this, we can see that the TVS diode clamps our voltage to our DUT to 24 volts, quite easy to protect downstream. The current maximum across our discharge tube is 51 amps, which is a very easy rating to meet with a discharge tube. And then our TVS, instead of it being over 5-6 kW like it was earlier, it's only less than 3 kW. Still a lot, but less than half of what it was before. So what's actually going on here? So if you see there's this little spike right here, right where the gas discharge tube activates. These are slow acting devices. So when the surge is first shown across here, the TVS diode conducts almost instantaneously. It is able to dump the initial current until the discharge tube wakes up, essentially. Once it starts conducting, it takes the brunt of the force or the brunt of the power, making it so your TVS doesn't get destroyed. If we increase the size of this series resistor, it essentially will make the discharge tube take more of that power and the TVS diode to take less. By adding an inductor, you also have the effect of making the discharge tube take more of that power. And there are a lot of variations to this circuit that you can do. You can have a full pi filter in here to make sure that not only are you helping with the surge event, but you're also helping to prevent any ringing and to just provide a good noise filter both downstream of your circuit and back upstream on the conducted noise if you have a buck converter or something that might be spewing noise back to the circuit. There are also ways in which, and this will probably be another video I'll do, of having a E-fuse or a back-to-back MOSFET array in conjunction with this circuit to help disconnect the rest of your circuit on the event that there is a surge too great or too powerful for this main 3-layer approach to be able to protect against. So there you have it. There's a few different methods in which you can protect the input power supply going to your circuit board from surges or EFT events. I know I didn't cover these in a whole lot of depth. I was trying to keep this video pretty short and just give kind of big picture overviews of what you can do to protect a circuit. If there's anything you would like me to go into more detail in a follow-up video, please let me know. I'll almost certainly have a follow-up video on the discharge tubes, as well as talking about the E-fuses, which I didn't really get into in this video. So I really appreciate you guys for watching, and I will see you next time.